In this work, we provide new classical and new quantum algorithms for solving some variants of the subset sum problem based on dynamic programming technique. Let me start by defining the problem which we studied in our paper. And let me remind you first what is the subset sum problem, which is a well-known NP-complete problem. The input is a multiset of n integer value and a target value m. And the goal is to find or to decide if there exists a subset S of indices such that the summation over this subset is exactly equal to the target value m. One possible variant of this problem, which we call shifted sum, which is one of the main problems studied in our work, consists of the following task. Again, you have as input a multiset of integer, and you have a shift value S. And now the output must consist of two different subsets, such that the summation over those two subsets is the same up to the shift S. As a particular case of shifted sum, there is the equal sums problem in which the shift is equal to 0, meaning you want to find two different subsets that sums to the same value. Another particular case, which we are also studying in our work, is what we call pigeonhole equal sums, in which you have an additional assumption, which is the sum over all the elements of the input set is at most 2 to the n minus 1. And by the pigeonhole principle, this condition implies that there must exist a solution to the problem. And it turned out that by using this extra assumption, we can obtain even more efficient algorithm than in the general case. But now let me show you what are the results, the main results that we obtain in our work. And let me start with existing prior work. So I should say that in our work, we focus on worst case input. For average case input, there exists more efficient algorithm. So for subset sum, the best known complexity as a function of n is obtained by the well-known meet in the middle technique. And classically, it gives 2 to the n half and quantumly 2 to the n third. And if the strong exponential time hypothesis is true, this is essentially the best complexity you can achieve classically. For equal sums, there is also a way of adapting the meet in the middle technique, and quantumly it gives you the following complexity. And classically, it has been shown recently in 2019 that you can do something which is more efficient than meet in the middle, and you can achieve such a complexity. Our algorithm will use some of the same ideas as what has been used for obtaining this classical complexity. This is now a summary of the main result of our paper. So first, for subset sum, we are able to obtain the same complexity as the best known algorithm by using a new technique which is not based on meet in the middle. For shifted sum, we generalize the complexity achieved for equal sum to this more general problem. And in the quantum setting, we obtain a complexity which is better than what was known before for the particular case of equal sums. Finally, for the pigeonhole equal sums problem, which is a particular case of shifted sum, we can improve even further the complexity by obtaining those two results. So all of our work are based on similar ideas. And for the rest of this talk, I would like to give you a general presentation of the algorithm for shifted sums in the quantum setting, which I think is the most interesting one. So the starting point is for solving the shifted sum problem in our paper, is to use the so-called representation technique, which is now a standard technique in the design of average case algorithm for solving shifted subset sum, but which was only be used recently for equal sum in a worst case analysis. This is how this technique will be used in our case. A first step will be to select a number p according to some rule I will explain later on, and to hash all the possible subset sum value into bins indexed by value k, with k being between 0 and p minus 1. And the bin will just contain all the possible subsets for which the summation is equal to k modulo p. The second step is to select a certain number k, the index of a particular bin, and to search if there is a collision inside this bin, which means if there is a pair of subsets such that the first one is in the bin k, the second one is in the bin k minus s modulo p, and the summation are equal up to the shift s, which is a condition for being a solution to shift sum. So the advantage of this technique is, in some sense, we have reduced the search space to a single bin. But of course, by doing that, we can miss a collision. So there are basically two conditions that we must satisfy for the algorithm to work and to be efficient. The first one is we want the bins to be sufficiently small to keep the search of the collision efficient. And the second condition, which is more complicated to achieve, is that we want the bin that we selected to contain a collision with high probability. And this is usually for satisfying the second condition that we need to use some average case analysis technique, which we cannot use in our case because we have worst case input. So how can we obtain this second condition? For that, we need to introduce two important concepts. The first one is what we call the set of collision values. It's a set of integers denoted by v. And it contains all the value v that can be achieved by a solution to the shifted sum problem. Meaning for each solution, the value of the first subset is one collision value. The second concept which we need is the maximum solution size, denoted by gamma. It's a number between 0 and n. And it is the size, the cardinality of the largest possible disjoint solution to the shifted sum problem that we are considering. And there is a strong relation between those two concepts, which is provided by the following inequality, which say that the number of distinct collision value, which is the cardinality of the set V, is at least 2 to the n minus gamma. In other words, when the maximum solution size is small, you can have a much more distinct collision value. So why this lemma is important? It's not very complicated to prove this lemma. And it's important because the larger V is, the higher the probability of having a collision in a random bin should be. So let me now give you the algorithm that we designed based on this simple analysis. And one of the most important tools in our algorithm for obtaining a quantum speedup compared to the classical setting will be to use the so-called quantum element distinctness algorithm, which is an important algorithm discovered by Baynes in 2007. And it gives you a quantum speedup for solving the task of finding a collision in an arbitrary set of values. So let me illustrate how we can use this element distinctness algorithm to obtain a quantum speedup in our case. In the particular situation when gamma, the maximum solution size, is exactly equal to 3n over 5. This is a simpler case to analyze. So because of the analysis that I showed you in the previous slide, we know that there are at least 2 to the 2n over 5 distinct collision values. And this is how we choose P and K in this particular setting. P is going to be a random prime number of order about 2 to the 2n over 5. And K is going to be a uniformly random integer between 0 and P minus 1. So because of this choice, the expected size of the random bin indexed by P and K will be about 2 to the 3n over 5, because we have two to the n values being hashed in p random bins. And because p is of the same order of magnitude as this lower bound on the number of collision value, then we know that a random bin will contain a solution with high probability. So we won't have to sample many value of k before finding a collision if there is one. And finally, we just have to find a collision in this particular bin. And for that, we'll run this element distinctness algorithm on this bin and the bin shifted by S modulo P. And the quantum speedup that we obtain, so classically, for finding such a collision, you will have to explore the entire bin in the worst case. So the complexity would be linear in the size of the bin. And quantumly, the complexity is the size of the search space to the power of 2/3, which here would give you 2 to the 2n over 5 steps for quantum element distinctness. There is, however, a subtlety in this algorithm, which is that for implementing each of those steps of quantum element distinctness algorithm, you would have to perform one query to the bin TPK that you picked. And what's a query? It's just the following thing. Given some arbitrary indexing of the element in the bin of index k, you want to be able to implement the following oracle, which takes as input an integer L between 1 and the size of the bin, and that returns the else element in the bin TPK. And the cost of implementing this oracle will have to be multiplied by the number of steps to obtain the final complexity of the algorithm. It turned out that implementing such an oracle is not a simple thing to do, because this set is of exponential size, and there is not even a simple way of ordering it or accessing the element in this particular set. So for constructing this oracle, this is where we need to, where we have to use dynamic programming, and this is what I'm going to explain now, how to implement efficiently such an oracle. And for that, we'll start by constructing a particular table in which the entry ij will contain the number of subsets with value in 1 up to I, such that the summation is equal to j modulo p. Okay, and it contains the cardinality of this set. So the last column of this table, as you can see, will contain the cardinality of all the possible bin TPK. And by dynamic programming, it's a simple exercise to prove that you can construct it in time about the dimension of the table, which is n times p, which is a lot because p is exponential. However, you will have to construct it just once. Then we define a particular total order over the possible random bin. The definition is not that important. What's important is the following result, which says that if you choose a particular bin TPK and query index L, and if you have access to the random, to the table constructed by dynamic programming, then you can reconstruct the else subset according to this order in time linear in n, which is extremely efficient. It's basically negligible compared to the other steps of the algorithm. And this oracle is quite simple to implement. So this is the code for the oracle. And basically the idea is to start from the last column of the table and to go backward to decide if each element between 1 and n should be included or not in the set that we are reconstructing. And as you can see, this table that we have to construct by dynamic programming is independent from k. So this is why we don't have to construct it many times if we want to try different value of k, for instance. So let me conclude by giving you the final complexity for shifted sum in the quantum setting. So in this graph, the x-axis represents the maximum solution size gamma divided by n to obtain a number between 0 and 1. And the y-axis corresponds to the exponent in the running time. So what I just showed you is for gamma being equal to 0.6 times n, we can achieve a complexity of 2 to the 0.4 times n. The black curve represents what you can obtain by applying the meet in the middle technique to the shifted sum problem. So this is like the folklore algorithm. And now this is what we obtain for other value of gamma if you extend the technique I showed you to other value of gamma. And there are basically three different regimes of parameters. So first, when gamma is close to 0 or n, the best we know how to do is just to apply meet in the middle. So correspond to this part on the right and this part on the left. The second regime is when gamma is smaller than 0.6. In this case, we combine the representation technique with a new quantum algorithm that adapts the quantum element distinctness technique to the case where there are many solutions to the problem. And in that case, we can obtain something which is more efficient because of the existence of many potential solutions. Finally, the last regime of parameters is when gamma is larger than this value, in which case the number of distinct collision values is becoming smaller and smaller. And for that, we need to boost the success probability of sampling a good random bin. And for doing that, we apply another quantum tool, which is called variable time amplitude amplification. And the worst case complexity is achieved when gamma is about 0.8 times n, and gives you something which is slightly above 2 to the n half. Let me finish by giving you just one open problem. So as I said at the beginning, for the particular case of pigeonhole equal sum, we can obtain something even more efficient. We also try to adapt our result to another problem called pigeonhole modular equal sum, which is defined here. And for that problem, it turns out that we don't know how to obtain a quantum speedup compared to the classical setting. And we believe that this is an interesting open question. Thank you for your attention.